students, now I am discussing non-degenerate energy level. Further, we will use Schrodinger equation. The Schrodinger equation is H psi is equals to E psi. We know that H is the Hamiltonian operator and E is the energy operator. Further, we can also write eigenvalue equation. That eigenvalue equation can be written with H ket of psi is equals to E ket of psi. So we know that the Hamiltonian total Hamiltonian is given as H equals to H naught plus lambda H dash. We know H naught is the unperturbed term and H dash is the perturbed term. So this equation we have derived already. We discussed this. Next, we are writing the ket of psi n be the eigenfunction of H at En. This one we can write this equation as H of psi n is equals to En ket of psi n. So expanding this En energy term and the wave function term, how we are expanding the series of power lambda. En equals to En of 0 plus lambda En of 1 plus lambda 2 lambda square En of 2 and so on. Here we are just next expanding the psi n term ket of psi n, which is a wave function that can be expanded as psi n of 0 plus lambda psi n of 1 plus lambda square psi n of 2. Here these all terms represent the zeroth order, zeroth energy level, first energy level, second energy level. Here first wave function, second wave function, the third wave function. Now next we are substituting these two equations in equation 2. In equation 2, H in the place of H, what we can substitute? The value of H naught plus lambda H dash. And similarly in the place of psi n, ket of psi n, we write this one, and it is equals to En value. We know this En of 0 plus lambda En of 1 plus lambda square En of 2. Yes, here we are not writing the equals to up to so on. Why? Because first term lambda here the perturbation is high. Suppose it will be high, means if the perturbation is 1 by 2, when it is going on second order, its perturbation is goes on decreasing, then it will be 1 by 4, and next 1 by, if we write lambda cube, it will be 1 by 16, means its perturbation goes on decreasing. So just we will, for calculating, we will take only the second order up to second order. So here we are not writing up to so on, but here we kept up to so on. Okay, next we are substituting again the ket psi n value. So next step, how we get this one means here we are comparing the lambda coefficient, but first step we are not comparing the lambda coefficient and the constant term. Now we are comparing only the constant term. Here the constant term is H naught psi n naught, and here no, everything is a coefficient of lambda c. Next, which is equals to psi En of 0 psi n. Here also all are lambda terms, so we are leaving that all. This is the zeroth order perturbation, and next we are equating the lambda terms. So here lambda term, how we can equate? Here in this equation, H naught lambda psi n. This one we can't equate because the lambda square term. We are equating the lambda term H naught psi n of 0 plus here lambda term we can write H dash psi n of 0, this psi n of 1, which is equals to this side again here lambda square. We are only equating the lambda term. Okay, here again we can write En of, here lambda is there, so we can write En of 0 psi n of 1. Next one, lambda En of 1 is, which can be, if we multiply with this is the lambda term En of 1 psi n of 0. The zeroth order perturbation and the first order perturbation. This is only for the non-degenerate energy level. Now we will find, for first order we will find the first order perturbation for energy En and first order perturbation for wave function psi n. First of all we will find first order correction to the energy En. We can say correction or perturbation or any disturbance, small disturbance. So further we are considering the equation. Which equation? Already we have done that equation. This is one, H naught psi n of 1 plus H1 psi n of 0 is equals to En of 0 psi n of 1 En of 1 psi n of 0. This is the first order perturbation. For first order perturbation we are finding the energy, that is En of 5. we know this equation. For this equation, we are multiplying this equation from left side by the bra of psi n of 0. Then we can write this multiplying this equation with bra of psi n. So see here h, so bra psi n h naught psi n dash plus same here bra psi n h dash psi n of 0 is equal to E n naught psi n. Again here also multiplying with bra of psi n plus E n dash here psi n naught. Next, we know that here h naught is a Hermitian operator. So the condition can be written for Hermitian operator is that this equation is there, this term psi n of h naught is equal to psi n of 1 is equals to E n of 0, E n naught bracket of psi n of 0 and psi n of 1. So this can be written in this form because we know this condition h psi equals to E psi. We know the condition h psi equals to E psi. So using this condition, we can write h psi is equals to E psi or equal to E psi E. So now, so we are writing in the place of this one, we will substitute this. So now this equation become En, this equation. For this equation, I am writing instead of this one, En of 0, so En naught psi. So this one I am writing now instead of this psi n of 1 bracket of psi n of 0 and psi n of 1 plus remaining the same term, remaining the same as it is. So now this we are cancelling out the two terms, this term and this term. So what we will left, so we will left with this only the this term bracket of psi n of 0 h dash psi n of 0 is equals to En of 1. Why we are saying 1 here? Because here there is a normalized function psi n of 0 bracket of psi n of 0 whose value is equals to 1. So we are writing it as a 1. So in simplified form, this equation can be written as En of 1 is equals to bracket of n h dash n. So instead of psi n, just we are using this term n. So this is the correction, first order correction for the energy, only for the energy. Next, we need to find first order correction for the wave function. This will be explained in the later class.